And now let's turn the above separation into an inpainting algorithm. Why are we connecting the discussion on inpainting to the one on separation? Because this connection was made in this paper. The idea the authors came up with is this. We do know how to inpaint cartoon images by forcing smoothness and continuing edges. We also know how to inpaint textures by texture synthesis techniques. These are two very different methods, and each is suitable for its own content. So, given an image that has both contents, we separate, inpaint each part with its own appropriate method, and then merge back. This is exactly the idea advocated in this paper by Bertalmio, Veze, Sapiro, and Osher. Okay, so we will try to do the same, exploit the MCA separation for inpainting. However, before doing so, let's come back to the fundamentals and present the essence of the inpainting problem in the context of SparseLand. Suppose that a signal X is known to have a sparse representation with respect to a dictionary D. Now imagine that a nasty person comes and takes few of the samples from X. That means we know the location of the missing elements, but we do not know their original values. Missing values in X imply missing rows in our linear system. This can be described as a mask M multiplying the linear system. So we have in our hands a new smaller linear system, X tilde equals D hat times the very same alpha 0 we started with. This system has fewer rows due to the missing elements. If alpha 0 is still the sparsest solution of the resulting system, and we could find it by a pursuit, we could recover the missing elements perfectly. All that needs to be done is to multiply the complete D by this sparse vector alpha 0. So how can we bring this concept into the separation? Here is our separation optimization problem, and now all that needs to be done is to insert the mask operator as shown here. The idea is that we should force proximity between the image Z and the sum of the decompositions only in the known pixels, while disregarding the missing ones. The sparsity over alpha and beta should lead us to the completion. Once this problem is solved, dc times alpha plus dt times beta is the inpainted result. We would like to draw your attention to two things. First, this scheme is much simpler and more direct compared to the variational one we just saw. Secondly, observe that we do not care so much about the separation as it is implicit to our inpainting process. And here it is, working. Amazingly, a small modification in the MCA algorithm leads to all the results we are about to see. The original image with the mask is shown on the left, the separated layers are shown in the middle, and their sum is the inpainted result on the right. This is the same experiment but with a different mask, and as can be seen, there are no traces of the mask in the result image. Moving to tests on Barbara, we see on the left the two masks and on the right the recovery results, which seem to be near perfect. In this slide we show two kinds of tests. On the left, the holes are getting bigger, and with them the challenge grows. When the holes are too big, some artifacts are seen in the result. On the right, we omit randomly some percentage of the pixels. This is an easier case for which the results tend to be very good. We summarize. MCA was proposed for separation of SparseLand signals. We have shown how effective this scheme can be, both for separation and also for inpainting. Indeed, moving to inpainting required a near-trivial change in the algorithm. One flaw that do exist in all the discussion so far is the reliance on fixed transforms. We now turn to operate on patches so as to be able to use trained dictionaries.